Hello, students. We are back working with fifth period. We are today talking about section 4.3, law of multiple proportions. Um, Remember, all this information is in the packet. It's just in a PowerPoint form. Okay, so it is the same information that you should see here on the electronic version, but you're going to see it in a PowerPoint. Okay. Um, Today I'm working with fifth period. They're going to be helping me out with today's presentation. All right, so our introduction talks about what are the similarities and the differences between a unicycle and a bicycle. We're going to introduce today's topic using or talking about the differences and the similarities between a unicycle and a bicycle. Who's going to help me with introduction?
Just from the words themselves, the astute Latin-speaking scholar can tell that whatever it is made of, the unicycle has one of them. Uni equals one, and the bicycle has two. Bi equals two. From the picture above, we get additional information that helps us tell the two apart. The unicycle has one wheel and the bicycle has two. In particular, they are made up of the same materials, and the only significant difference is the number of wheels on the two vehicles. So now, how many wheels on a tricycle?
All right. Thank you, Miss Alexia. All right. So our introduction is talking about different versions of a bicycle, right? We know that there's a unicycle, a bicycle, and a tricycle. Okay. They all have one frame, right? The unicycle, the bicycle, and the tricycle all have a frame where the person sits on it, right? Now they're telling us, and you can tell from the picture that is in this that's in the slide, that a unicycle has one wheel, a bicycle will have two wheels, and a tricycle will have three wheels, right? Okay. And why is it part of our introduction today? Well, the law of multiple proportion says that if you have the same elements, if you have a pair of elements, right, you can make different compounds by having different proportions of each element. Okay? For example, water. Water is easy, right? Everybody knows water. Water is made up of hydrogen and oxygen. So we have hydrogen and oxygen. Water has one hydrogen, two oxygens. Okay? And if you've ever heard of hydrogen peroxide also has hydrogen and oxygen, but in different amounts. Okay? When it comes to hydrogen, there are two atoms of hydrogen. When it comes to oxygen, you'll have two atoms. All right? So, what's the difference between water and hydrogen peroxide? Not only the fact that hydrogen peroxide, you can't really ingest that. Water you can drink all day and night and you'll be fine. But when it comes to hydrogen peroxide, you can't drink that because it can be very dangerous. But both of those compounds contain the same elements, hydrogen and oxygen. Okay? So let's talk about a little bit more about the law of multiple proportions. Hi, Isael. Hi, America. I'm glad you can join us today. Once the idea of elements combining in definite proportions to form compounds was established, experiments also began to demonstrate that the same pairs of certain elements could combine to form more than one compound. And they want you to consider elements carbon and oxygen. Combined in one way, they form a familiar compound known as carbon dioxide. In every sample of carbon dioxide, there is 32 grams of oxygen present for every 12 grams of carbon. Where are these numbers coming from, miss? Okay. Well, if you look here, you have the formula for carbon dioxide. There is only one carbon, two oxygens, and oxygen, well, it weighs 16 grams, just one of them. If you have two of them, Well, you're going to multiply 2 times 16. That's where this 32 grams comes from. On the other hand, for carbon, one element of carbon or one atom of carbon weighs 12.0 grams. Okay, since there's only one in this compound, we leave it at 12. Okay. By dividing 32 by 12, by dividing 32 over 12 grams, you can simplify the mass ratio between oxygen to carbon to be 2.66 for every one. And you can see it mathematically here. Originally, you had 32. You divided it by 12. You get 2.666 divided by 1. There it is. 32 divided by 12 gives us the 2.66 over 1. Okay? That's the first one they're talking about. This is carbon dioxide. Carbon dioxide. Okay? There's another compound that carbon and oxygen can make. It's called carbon monoxide. And you have a picture of that atom or that compound on the right, on the picture on the top right. Every sample of carbon monoxide contains 16 grams of oxygen for every 12 grams of carbon, right? There's only 1 and 1. Carbon weighs 12, oxygen weighs 16. Okay. If we were to divide 16 by 12, there would be a mass ratio of oxygen to carbon to be 1.333 to 1. Okay? And I have that here. If you divide 16 by 12, you'll get 1.333 for every 1 gram of carbon. Okay? Good. Right? Good. We understand those numbers that they're talking about. In carbon dioxide, there is exactly twice as much oxygen present as there is in carbon monoxide. Yes, we can see that. Carbon dioxide has a 2 after oxygen. Carbon monoxide has a 1 after oxygen. This example illustrates the law of multiple proportions. Whenever the same two elements form more than one compound, the different masses of one element that combine with the same mass of another element are in ratios of small whole numbers. Okay? That just means if you were to divide 2.66 by 1.33, you would get a 2 over here. Okay, let me show you real quick. This is that whole number ratio that they are talking about. What's different about this compound? It's my oxygens. That is what makes these compounds different. It's not my carbon. So if I compare the mass, okay, and you can see here the mass, right? For oxygen on the top, 2.66. For oxygen in carbon monoxide, 1.333. You divide it and you get a small whole number ratio, which in this case is 2. All right. All right, you have your first interactive question. Those of you who are in Pear Deck from my 5th period. Carbon dioxide and carbon monoxide is used as an example to explain the law of definite proportions. True or false? Did we use carbon monoxide and carbon dioxide to explain or to use as examples for the law of definite proportion? What do you remember from the last slide? What do you remember? True or false? If you are not in Pear Deck, America, Irvin, Efrain, anybody who's not in Pear Deck. Oh no, Efrain said he was in. No, Arlette said they're in. So America, Irvin, Efrain, Melissa, true or false? In the chat right now. What do you think? True or false? Okay, America says it's true. Okay. Anybody else? Anybody else? True, according to Efrain. Is today's topic the law of definite proportion? Is today's topic the law of definite proportions? Irvin is the only one who's saying false. Is today's topic the law of definite proportions? And I'm going to go to the electronic version really quick. OMG. Look at what the topic is named. That is a false statement. Today's topic is all about the law of multiple proportions. That is a false statement. Okay? Today's topic is the law of multiple proportions. There's more than one version of these combination of elements.
Let's go, Miss. I was the only one.
Very good, sir. Okay, now, is this statement correct? You agree? Or is this statement incorrect? You disagree? The law of multiple proportions states, whenever the same two elements form more than one compound, the different mass of one element that combine with the same mass of the other element are in a ratio of small whole numbers. So you're comparing the mass of two versions of compounds. Okay? These compounds have the same elements, they just have different mass because there are different numbers of each. And when they do compare them, they're in ratios in small whole numbers. Agree or disagree? Is the statement correct and you agree? Or incorrect and you disagree? Is that the correct definition for the law of multiple proportions? All right. Irvin says he's agreeing. Alexia says they agree. Mario says he agrees. Let's see what they say in the Pear Deck. One person agrees and another person is somewhere on the top of disagreeing. So maybe he wants to lean towards disagree, but he's not 100% sold. Okay. Let's go back 2 slides. Whenever the same two elements form more than one compound, the different mass of one element that combines with the same mass of the other element are in ratios of small whole numbers. Yes, that is a correct statement, and I would agree. That is 100% right. Excellent job, Irvin, Alexia, Mario, and whoever this person was that chose agree. Whoever this person was right here. Good job. Excellent. Okay. All right. In carbon monoxide on the left, so you have a photo. We're talking about the left side of this photo. There is 1.333 grams of oxygen for every 1 gram of carbon. Okay. We saw that. We understand what they're trying to tell us. In carbon dioxide on the right, there are 2.666 grams of oxygen for every 1 gram of carbon. Okay? So the only difference between these two elements is not carbon, so we're not really going to take that into account. We're looking at the ratio between what is different. And in this case, the element that's different is oxygen. And if you divide, right? If you divide 2.666 divided by 1.333, you will get a ratio of oxygen in the two compounds being 1 for every 2. That is known as a small whole number ratio. The difference between carbon monoxide and carbon dioxide, okay, we know the ratio is 1 to 2, but their properties are very, very different. Carbon monoxide is a very deadly gas that forms when a combustion reaction doesn't complete. And you have carbon containing materials like wood and gasoline. This compound will attach to hemoglobin in red blood cells, block oxygen from binding to those cells, and prevent oxygen to be carried to the cells all over your body where it is needed, and death will eventually occur. Every time we breathe in oxygen, it's supposed to travel in our blood by binding to red blood cells, where it travels to every single cell in your body so that you can live. If that gets blocked, and carbon monoxide blocks that oxygen doesn't get to your cells, eventually you die. That's carbon monoxide, CO. Carbon dioxide, CO2. Not only is it the gas that we breathe out in the respiratory process, but it is also non-toxic. It can, however, displace oxygen in a system because it is very heavy. When you compare oxygen to carbon dioxide, oxygen is very light, carbon dioxide is very heavy. So if you have a carbon dioxide fire extinguisher, a carbon dioxide fire extinguisher, you can cut off that flow of oxygen, right, which feeds the fire, by using the fire extinguisher and eventually putting out that fire. All right. What is the whole number ratio between carbon dioxide and carbon monoxide discussed in the previous slide? And I believe this is a multiple choice question. A, 1 to 4. B, 1 to 3. C, 1 to 2. D, 1 to 1. What was the ratio that we just discussed in the previous slide between carbon dioxide and carbon monoxide? A, B, C, or D? One person has responded in Pear Deck. I still haven't gotten anything from the people in the Google chat. But I'm sure Irvin, he has been 2 for 2, Irvin. Are you going to be 3 for 3 or are you going to go 2 for 3? Are you going to get this one correct also? Right now, Irvin's on fire. Will he be extinguished or will he continue to burn? What is the small whole number ratio between carbon dioxide, carbon monoxide discussed in the previous slide? A, B, C, or D? I could already see Irvin flipping through pages on his packet and be like, what was the number? What was the number? Anybody else want to take a stab at it? Melissa, Efrain, Arlette, Kevin, Mario, Jose. Take a guess. Over here in the Pear Deck, I got 2 people who say that it's B. The ratio is 1 to 3. Efrain says A, 1 to 4. Irvin, I'm waiting for you. I want to see if you get this one right and you get 100% batting average. Yeah, Alexia says B. It's 1 to 3. Okay. Anybody else? Irvin, are you going to try and take a stab at it? Irvin says it's A. 1 to 4. All right, let's check it out. At the top paragraph, it says the ratio of oxygen in the two compounds is 1 to 2. That was letter C, I believe. Letter C. Wah, wah, wah. Good try, Irvin. It's okay. It's okay. The ratio, the answer was letter C. 1 to 2. Good try, guys. Good try. Maybe tomorrow will be better, Irvin. Maybe tomorrow will be better. All right, we got a video about the law of multiple proportions. They're going to use the same example that we talked about, carbon monoxide and carbon dioxide. Maybe you'll understand their version better than mine. Hopefully there's a commercial. Ugh, I hate commercials.
All right, now we're going to go over the law of multiple proportions. So this law, in addition to the law of conservation of mass and the law of definite proportions, provided strong evidence for the atomic theory as we know it today. So this law was proposed by John Dalton in 1804, and it says that when two elements, A and B, form two different compounds, the masses of element B that combine with a fixed mass of element A can be expressed as a ratio of small whole numbers. So that sounds really complicated, but it's really not. So that means if I have some compounds of the general form AB, AB2, AB3, etc. If I use the same mass of A for all three of these compounds, so suppose all three of these masses are all 1 gram for simplicity, then that means if I compare the mass of B in this compound to the mass of B in this compound to the mass of B in this compound, well, those ratios are going to be, I'll just call them X, Y, and Z. Those ratios are going to be small whole numbers. So let's go over an example of a real compound, and we'll examine this law of multiple proportions a little bit further. So I'm going to give myself some room here real quick. Just bear with me. So suppose I have carbon combining with oxygen. And carbon can combine with oxygen to produce more than one type of compound. So let's say carbon and oxygen can combine to produce carbon monoxide, CO, and carbon dioxide, CO2. So this would be, the CO would be like AB and the CO2 would be like AB2, for instance. So carbon would be A and oxygen would be B in this particular case. So suppose I keep the mass of carbon fixed at 1.0 grams. Well, since we know the mass ratio of these two guys, carbon monoxide and carbon dioxide, according to the law of definite proportions, there's a certain fixed mass ratio associated with each of these two compounds. It turns out that the masses of oxygen that have to combine with 1 gram of carbon to form carbon monoxide and carbon dioxide are 1.33 grams and 2.67 grams, respectively. So that means if I have 1 gram of carbon, I need 1.33 grams of oxygen to get carbon monoxide, CO. And if I have 1 gram of carbon, I'm going to need 2.67 grams of oxygen to get CO2. So now what we're going to do is divide the larger by the smaller. So if I take 2.67 grams of oxygen given from the CO2 molecule, and I divide that by 1.33 grams of oxygen given from the carbon monoxide, then I will get a whole number, a small whole number, which is 2. So that, in a nutshell, is the law of multiple proportions.
We get it. You don't really want your...
All right, let's finish up today's topic. Summary. The law of multiple proportions states that whenever the same two elements form more than one compound, the different masses of one element that combine with the same mass of the other element are in the ratio of small whole numbers. The 3 questions that we're going to answer before you go. State the law of multiple proportions. Number 2, in carbon dioxide, how many grams of oxygen would there be if there are 24 grams of carbon? Number 3, how many grams of carbon would be present in carbon monoxide that contains 2.666 grams of oxygen? All righty.